All right, so it's my pleasure to introduce Ben Southworth today. Um, Ben spent a lot of time at Livermore. I remember when he was a student here, and now he's at Los Alamos. He's been there for a while, doing a lot of interesting work in many areas that intersect FEM and the type of discretizations we're interested in. And today he's going to talk about discretization and solvers for anisotropic problems, if I remember correctly. Ben, thanks for coming. It's a real pleasure to host you. Please share and take it away.
Cool. Thanks, Daniel. Hello, everybody. So I'm at Los Alamos National Lab in T5, and I, as Sonia mentioned, work in a lot of different areas. My background is largely linear and nonlinear solvers, and lately I've been getting into time integration for coupled systems and things like that. Today I'm going to talk about discretizations and algebraic multigrid solvers for extremely anisotropic diffusion in the context of magnetic confinement fusion. And these discretizations and solvers are kind of constructed using principles from hyperbolic operators. And so this is joint work with Golo Weimer, who's a young staff scientist here in T5 also, and Shanji Tang, who's much more senior and works on magnetic confinement fusion. And then Tom Gregory was a summer student that did some of the results with us. And so I just also want to highlight that, as I said, I'm more of a solver person than a finite element person. I'm a user of finite elements, not a genius of finite elements or constructor of new things. And so I have to give a lot of credit to Golo for taking kind of this vision I had of a way to approach the solvers and work back and forth to facilitate solvers and discretizations that are compatible. And this is, to me, a super important area of research for hard physics that doesn't get enough attention, and that's getting compatible solver and discretization where you get the accuracy you need, and it's also still tractable for fast linear and nonlinear solvers. And it can be hard to do that. You can have a really good discretization, and it's not uncommon for those discretizations to also then be extremely difficult to solve using conventional methods. Okay, so this is the outline. I'm going to provide a little bit of background on the problem and anisotropic diffusion and different formulations of it. And higher perspective on how we motivated this use of hyperbolic operators. And then I'm going to talk about the spatial discretization in the DG context, the CG context, and then just some structure preservation comments on both types of discretization. And I'll talk about accuracy here. And then I'll move into the linear solvers part. And so this is a little bit backwards from how we did the research. The original idea came from the solver perspective. Then we did DG elements, then we came back to solvers, and now we're working on CG elements. And so I reorganized to try to make it a little easier to follow. Okay, so anisotropic diffusion. Most people know what this is. We have the evolution of temperature and plasma. Forget the heat flux for now because we're in second order form. We have some forcing term. And so here's our operator. And the way we write it here is we have split the gradients into kappa parallel and kappa perp. And so kappa parallel will be parallel with the magnetic field lines, so heat conduction following along the magnetic fields. And kappa perp is going to be orthogonal to the magnetic field lines. And you're right. And so what will be here is a normalized direction of the magnetic field. And so this is a common way to write it in second order form. It turns out when you have extreme anisotropy, this is also not a good way to write it. It's not good from the discretization perspective when you get into the really extreme anisotropy ratios. So there's many different ways to skin a PD, as you could say, or just to formulate it, right? I mean, you have to go back to the original problem and say, how are we going to write it out? And so another way that people use is to introduce a heat flux, right? So you have the first order formulation of your diffusion equation, and you write it in divergence form, with divergence of your heat flux, and then we have this forcing. And then here's your flux, and this is where the anisotropy comes in. And again, same grad parallel and grad perp as before. Again, this is common. It's still not quite what we're going to use here. We're going to use something similar in what we call, one more slide here, I forgot. When I say extreme anisotropy in the context of magnetic confinement fusion, it's really big. So the ratio is like 10 to the 9 to 10 to the 10 in terms of the ratio of conductivities in the direction of the magnetic field versus orthogonal. And so what's interesting about this problem when it gets this high in anisotropy is that the equation is parabolic in nature. I mean, or if you're steady, it's elliptic. But if you have a non-grid aligned magnetic field, it's really hard from an accuracy and the implicit solve perspective. And that's kind of where this project came from is, well, how do we solve this? And my background is in, again, algebraic multigrid, and I've worked on AMG solvers for anisotropic diffusion, and I thought we had pretty decent ones. And then I started working with these fusion colleagues and said, okay, give me some sample problems. I can try to set a solver for it. And turns out there's a little bit of a gap between what we do in the solver literature and what they really want to solve in their fusion problems. And what we thought worked well did not work well when we had a real problem. So what we're going to use for actual formulation is a directional gradient formulation. So it's still effectively first order form, and we still have this heat flux. But what we do is we separate our conductivities into an anisotropic conductivity, so this kappa delta here, and then the isotropic conductivity is everything that's left. And so if kappa delta is 0, then diffusion is isotropic. And for kappa delta much bigger than kappa perp, then it ends up being predominantly anisotropic. And so then instead of using the heat flux as an auxiliary variable, we actually use a directional gradient. So it's v dot grad t scaled by the anisotropic conductivity. This ends up being our auxiliary variable. And so then this is the kind of continuous form of the equations. We have a first order form for the anisotropic component, so here and here. And then we have a second order form for the isotropic diffusion. And this is kind of separating off the difficult part from the part that we know how to solve. Everybody can solve isotropic diffusion from a discretization and solver perspective. And so to kind of get into the motivation of where this all came from, if you write out this formulation in a block operator form, so forget your discretization for now, just keep the strong form of differential operators. We have our temperature, we have our auxiliary variable, and up here we have our time derivative and temperature and our isotropic diffusion, and then our off-diagonal operators end up being these directional gradients. That's how we formulated with this coupling. This coupling between them. And in a finite element case, this would be a mass matrix. And so if we look at this and say, okay, let's take a limit, right? Let's take the anisotropic limit, because when we get to 10 to the 9 ratios, we're almost 0 isotropic diffusion anyway. And let's say we skip the time derivative. So we're just going full steady state, fully anisotropic diffusion. If we write it out like that and rearrange the system, it's equivalent to this form here. And so instead of a diffusion system now, what we really have is two coupled hyperbolic operators. Directional gradients in the direction of magnetic field coupled with this mass matrix. And that's this limiting asymptotic of our system. It's in the case of steady and no diffusion in the isotropic setting. And so this is kind of my original vision is I tried some solvers on the anisotropic problem, classical AMG formulations, things like that, with tailored AMG methods for anisotropic diffusion, and it just did not work. It just did not work. And so I said, well, what if we rewrite the system and pose it in terms of hyperbolic operators and focus on solving that? Because the other big background that I have is I worked a lot on AMG methods for transport. That's a big focus of my thesis and the research thereafter. And so if we rearrange the system and think about it like this, we can apply this specific AMG solver I have to these equations. It's very fast and effective and with the right discretization context. And then we don't have to worry about the anisotropy. Instead, we kind of solve these advection operators with separate techniques. And so that's kind of big picture in this regime of extreme anisotropy. I am kind of claiming that we should really treat this parabolic equation as a system of coupled hyperbolic operators rather than a parabolic operator. And that's not a common thing to do. Parabolic equations and elliptic equations have so many nice properties. It's not necessarily intuitive to move away from that into the regime of hyperbolic operators, which have 0 nice properties. But it actually can be very useful in this regard. Okay, so that's kind of big picture. Now I'm going to talk about the spatial discretization, and I'm going to start with discontinuous Galerkin finite elements. So most people here are probably familiar with the standard upwind DG discretization of transport. And so that's what we use to discretize our directional gradient here. So this is our weak form for our transport in one direction, and we have our element integral, and then our facet integral here. Gamma, we used capital gamma to define the set of all interior facets. We have upwinding using this twiddle here. And then we have our outflow boundary condition for this direction of transport. And we have the standard jump notation. And the reason we did this originally, again, this is kind of trying to make compatible solvers and discretizations, is we had this idea, okay, let's try to solve the transport operators. And like many solvers, air, which is what I'm going to use and I'll talk about later, is finicky. It doesn't work for any advection discretization. It really works really well for upwind stabilized discretizations. And so I told Golo, we should try to treat this transport term using an upwind discretization because that's what we can solve. And so the full weak form, we have two transport operators, all right, one on each off diagonal of our coupled 2x2 system. And there's one nuance here in that when we pose it as a transport operator, we need transport boundary condition, right? If we just consider discretizing the first order gradient without a time derivative, we can't pose boundary conditions on the whole domain. And so we need an inflow boundary condition. And for one of the transport operators, this is fine. It ends up being naturally extends from the boundary conditions of your temperature. For the other one, we introduce this zeta in here, which is we kind of assume to be known. And the whole purpose of this, again, is if we know the inflow boundary conditions, then this ensures that these operators are invertible. If we want to apply algebraic multigrid to the advection equations, they need to be invertible, at least for now. We'll talk more about that later. And so there's two ways we can do this. One of them is simple. We just iterate within a Picard iteration implicit solve until we have this inflow boundary condition equal to the solution zeta h. And here we just want to comment right now we're focusing on a linear formulation of the problem, but really in anything practical, this is going to be a full nonlinear equation in T, where the diffusion coefficients really depend on the temperature. And so within the nonlinear iteration for T, we're like 99% sure that this right here is less stiff and easier to resolve than the actual temperature nonlinearity. And so we think that we're going to get this for free when we go nonlinear. In the meantime, we're doing it in kind of an implicit-explicit approach where we just treat the auxiliary inflow explicitly. And interestingly, we found this to be it varies slowly in time, it's non-stiff, and we haven't had any problems with that kind of implicit-explicit treatment. So we could include it in an outer iteration if we want to. Right now, we don't do that. And so these are our two transport operators. And then the full weak form of our directional gradient formulation in the mixed DG formulation is given here. So we have our time derivative, we have our transport operator in the primary variable in temperature. IP, this just stands for a typical interior penalty discontinuous Galerkin discretization of the isotropic component of diffusion. Here we have a boundary integral and forcing term, and we have our auxiliary equation here with our other transport operator. And so again, here we choose the order of our DG spaces to be equal to ensure square invertible diagonal blocks, right? If we choose different order elements, then our off diagonal in the mixed system end up being non-square and not invertible. And so this is the weak form. And I'm going to show that it works. So we formulated a kind of MHD test problem. It's motivated by problems in magnetohydrodynamics, but we want to get rid of all the other physics for now and really just focus on the discretization solver of the diffusion. So we define a 3D domain that's periodic in Z, kind of roughly simulating the tokamak situation you would get in magnetic confinement fusion. And we start with this initial temperature here. And it's effectively a manufactured solution. And we choose our magnetic field to align with the contours of T naught and be constant in the Z. And so this is just how you do that. And what this does is ensures that the 2D curl of your initial temperature is given by your B field. And so what we do is we can add a counterforcing term, again, the manufactured solutions, to ensure that the actual time, the continuous time evolution of this equation is really a steady state test case. And so in doing that, we can measure the discretization error over time and how it accumulates relative to some known solution that we should be at. And so this is how we measure the error. And so what we compare with is three different systems. We have a CG primal system, so that's continuous Galerkin, second order elements in the typical second order formulation for the problem. We do the same with the DG primal system, and so this has been used recently with some papers using FEM, and also Chris Vogel and Milan and Elon looked at AMR using this kind of discretization. And then we use a mixed CG formulation. So this was the original directional gradient formulation in the literature as far as we know. This was maybe 10 years ago or something. A paper Gunter et al. Proposed using this directional gradient formulation, but they do not use any transport discretization techniques. So they do a mixed form, and they use kind of standard CG and DG basis functions and mixed formulations to formulate the system. And so they use CG2 and DG1 in the auxiliary space. Okay, and so here are the accuracy and results for our DG discretization applied to this, kind of manufactured solution test problem. And what we have is a relative L2 error, and the three plots correspond to the anisotropy ratios. So on the left, we have 10 to the 3. This is not so bad. It's not realistic in the magnetic confinement fusion test case, but this is kind of what I thought might be a realistic problem before I got into the fusion problem. So I had AMG solvers that could work well on this, and we see that the accuracy also for the discretization works well. Then we go to 10 to the 6 and 10 to the 9, and that's where we were very pleasantly surprised to find not only does the stabilization and upwinding make sense and work well for the solvers, it actually helps substantially for the discretizations. And so in this far right plot where we're at 10 to the 9, which is, again, the kind of ratios we expect to see in practice, we're getting 3 orders of magnitude more accurate solutions using, oh my gosh, what happened? Sorry. 3 orders of magnitude more accurate solution using the new mixed DG scheme than any of these other 3 fine element formulations. And these aren't even converging at proper order yet. As you continue to refine, I expect they eventually will. They're starting to find that convergence, but it's taking quite a while to get there. Okay, and so that's DG. And we have a paper on that one online right now. And the paper discusses the DG element formulation and then the initial solver framework too. But before we get into the solvers, I'm not going to talk about continuous elements, which is what we started working on this fall. And so this is kind of ongoing work, but the idea is basic. It's that, well, we have this new DG discretization that not only worked for the solvers, but actually provided very good accuracy. And we use a similar formulation in the continuous element case. And so here, for ease of notation, I just dropped the isotropic component. It's exactly the same as DG. We use kind of standard continuous Galerkin fine element discretization of the isotropic part of the operator in the primary variable equation here. So we let VT be our kth order continuous Galerkin space, and then these boundary condition spaces and auxiliary space. And so here, this is our weak form. Again, we dropped the isotropic components. So we have these 2 transport operators, directional B dot grad eta and B dot grad T in the auxiliary equation. And then here, in principle, you can choose whatever auxiliary space you want. It can be CG or DG with different orders. Similar to DG, for the purposes of focusing on the advection solver, we choose the auxiliary space to equal that of the temperature space. And that way we have square advective blocks that, in the case of open field lines, are invertible. And so transport stabilization, we discovered that it works really well from the discretization perspective for DG elements. So we're going to try the same thing here. And the kind of analog that we're working with is using SUPG stabilization. And so to do this, we define our velocity field S as effectively the scaled, the appropriately scaled magnetic field direction. And we have the SUPG stabilization parameter tau, and we define 2 SUPG operators. We call them the advective and the flux-based SUPG operator. And they're similar, and one is just the tau is inside or outside of the gradient. And so then the mixed CG stabilized discretization in weak form is given right here. And a lot of it looks like what you might expect. It's just like the previous weak form, but we've introduced our stabilized operators. And then we now have this boundary integral as well. But everything else is kind of as you would expect. And so a few comments on that. The boundary integral appears because even though eta vanishes along the Dirichlet boundary, the SUPG modifications do not. So when we use the stabilized operators, we need to add a boundary integral to enforce that in the solution space. We choose this kind of averaged stabilization parameter for tau. This is kind of taking two different commonly used stabilizations. So one of them is the more or less the velocity speed divided by the mesh spacing, and the other is a scaling of the time derivative, and combine them both and take the inverse. And so I should say I introduced those two specific forms of our SUPG operators, our advective and our flux-based SUPG. These were chosen very particularly for structure preservation and consistency. So I'll get to that in the last slide, but we had a few structural properties that we wanted to preserve in our discretization. And so we started there. And then in doing the derivations, we kind of worked out exactly what SF and SA need to be in the weak formulation to satisfy these properties. Well, and then finally, in practice, we use weak boundary conditions for the continuous Galerkin formulation. And this is non-standard. Typically, if you use CG, then you use strong boundary conditions. But you have to remember that when we're doing this, a big part of the algorithm is swapping the rows of the assembled system so that in the mixed formulation, the mixed operators are actually on the diagonal. And at least in Firedrake, I know, I'm sorry, we're using Firedrake for this testing, but that's where Golo was working at the time, and it was easiest for him to implement things. It's non-trivial, and by that I mean we have no idea how to form the correct block row swap system with strong boundary conditions. Because as nice as UFL language is for finite elements, to get in and modify the matrices and the resulting system is a pain. So we will be moving to FEM at some point in the foreseeable future, and perhaps this will be easier to do in FEM. Okay, and so again, we have a new test case here. It's a little bit different. Here we have what we call a magnetic surface test case. So in magnetic confinement fusion, plasma gets trapped in these series of concentric tori going around. And so what we do is we unfold all these into a 2D surface and make it periodic. Sorry, not periodic. Yeah, periodic. We pretty much unfold it and we use a rational winding number. If you're a plasma physicist, you have a good idea what this is. Don't ask me for a good explanation because I don't have one, except for that if it's rational, the heat stays along certain structures. If it's irrational, eventually it will fill up the whole domain. So we have a rational winding number and an initial temperature perturbation, and we watch how it spreads on the surface. And so here we choose actually zero isotropic diffusion, and then everything's in the anisotropic direction. And so this is in some sense harder and easier. The problem itself is easier than the previous one, but we stay in the fully anisotropic regime. And we integrate out to 1 alphane time. And so again, here's the accuracy on the quads. The purple triangles, that's Q2. So we just mean here standard second order CG discretization applied to the second order operator. The red triangles are mixed. So that's the Gunther et al. CG2 discontinuous Galerkin 1. And then the green is our new mixed stabilized CG2 discretization. And so on quads, we do well. We're about a little over an order of magnitude smaller error than these schemes, and overall it looks really good. What's interesting is it looks a lot better with triangles. I'm not sure why these existing schemes struggle on triangles, but they do. They prefer the quads a lot, and our new scheme is pretty much indifferent. From a computation perspective, I appreciate triangles because everything's affine and it makes it easier to assemble things, or cheaper anyway. So here we're getting, at this point, not quite 2 orders of magnitude, but pretty close, better error using our new discretization than existing methods in the literature. Okay, and what time do we have? Good, lots of time. Okay, so the last part on the discretizations is to talk about structure preservation a little bit. So this is Golo's background is in structure preserving finite elements, specifically in terms of, I think, atmospheric sciences and geosciences. But it's good to think about these things, and it's been nice to talk to him about it. So consistency, this is a simple one. We have the CG and DG spatial discretizations that we developed are both consistent in the sense that a solution satisfying the continuous equation also satisfies the discretizations in the weak form as long as you have sufficiently regular test functions. And this is not uncommon. I mean, most discretizations would satisfy this consistency property, but when you get into the realm of stabilizations, then that's not always the case, right? If you introduce some kind of hyperdiffusion or things like that, which is relatively common in plasmas, then you lose that consistency. Okay, so diffusion is the next structural property where we just look at the magnitude of the temperature in the L2 norm as a function of time. And so continuous system satisfies this kind of structural property where it's dissipative up to the forcing terms. That's this TF right here. Sorry, we changed notation from an S to an F. So dissipative up to forcing term, and then the total in and outflux. So we have influx, outflux here, and then this is actually our magnitude of dissipation, so the change in time, right, of the total temperature. And the DG discretization satisfies this weakly, and so that's in the sense that this diffusion property is satisfied up to a weak boundary condition penalty. And so if you have a strong solution that satisfies the boundary conditions, then it satisfies the diffusion property. And the CG discretization with Neumann or weak Dirichlet boundary conditions also satisfies this weakly. And I also emphasize weak Dirichlet boundary conditions because even if we were to impose strong Dirichlet boundary conditions, which we don't in the code, you can't really satisfy these kind of properties with strongly enforced boundary conditions, I think. Okay, and then the other structural property that we care about is the total energy and temperature. And so the continuous system conserves total temperature, again, up to forcing and total in and outflux. So we have our forcing integral here over the domain, and then we have the flux through the boundary of the diffusion. And so, again, the DG discretization will satisfy this weakly and up to normal continuity of B. So effectively, as long as you have a magnetic field with sufficient regularity and a strong solution, then you satisfy this property in the weak sense. And then the CG discretization with Neumann boundary conditions automatically satisfies this. There's no weak aspect about it. And the CG discretization with, sorry, how do I go back? Okay, well, so the background is my keyboard is not plugged in so that my camera can be plugged in. So the final point of the structure preserving slide was that CG discretization with weak boundary conditions also weakly satisfies the temperature structural property. And it's a little more complicated. You have a bunch of terms that come out of the stabilization, extra terms. But again, if you have a strong solution, those terms drop out and you go back to the continuous structure preserving. And so on that note, before I move on to the next example, we have a nice video to kind of show this structure preserving property of mixed CG without stabilization and mixed CG with stabilization. And so this is that magnetic surface test case where we have these concentric tori that we unfold and we want to watch heat propagate along them. And so as time starts to progress further, what happens is the non-stabilized discretization on the left loses a lot of heat. There's a lot of temperature loss and a bunch of kind of funky oscillations that start to happen in the direction of the transport or of the diffusion. And our mixed discretization with stabilization maintains temperature quite well and is very consistent with these tori field lines. Okay, and so we have another example showing us a similar concept. So the spurious heat loss, this is a concern in simulating tokamaks and fusions that you don't want to be artificially losing temperature when you should be there. And so here, what we did to test that is, again, we set the isotropic diffusion to 0, and we took a physical value of the field, magnetic field line diffusion from a Brzezinski model, and we fixed the Dirichlet boundary conditions. And we did a relatively long time simulation. And this is something that comes up in plasma and fusion, is that you have to simulate relatively long time domains relative to the Alfvén time on which you're probably time stepping. And so we have periodic and angle, so it's goes around a circle, and then we have a CG discretization and DG discretization. And so what we get is the spurious temperature loss for different discretizations can be quite significant. So on the x-axis, we have alphane times, and we compared all of our different discretizations with the relative norm of T. So this is the total temperature integrated over the domain in an L2 norm. And so if we use a primal variable formulation, CG2, DG2, we're losing 40% or more of our temperature over this relatively, not super long, but longer time simulation. And then the mixed formulation does better, but still loses a lot of temperature over longer times. And these new schemes are created, both DG2 and then CG2 mixed and stabilized, we lose very little. We lose less than 3% with the continuous and less than 5% with the discontinuous. Okay, and so that's the spatial discretization side. And again, I want to thank Golo for doing a lot of the nuanced tuning and getting things to work just right with the stabilization. But it came out really well, and it was one of those fun parts of research where you enter with one goal and you find something else cool along the way. And so now I'm going to talk about the solvers that we use to solve the resulting linear systems. So to start, algebraic multigrid, this is what I've worked on a lot. And when it's applicable, it's one of the fastest algebraic methods to solve large, sparse linear systems, AX equals B. And algebraic multigrid has two parts, relaxation, coarse grid correction, and they're supposed to be complementary. So relaxation takes this form, xk plus 1 is your previous iterate, plus M inverse, where M is some relatively easy or cheap to apply approximation of A inverse times your residual. Oh, come on. And then coarse grid correction is similar, but now this M inverse is replaced by this operator right here, where we restrict to a subspace. We define a coarse grid operator in the subspace, and we invert it, and we interpolate the result back up. And so again, this is just an approximate inverse of A, but it's done by restricting to a subspace. And so if we look at error propagation of these two operators, so as you apply them, how the error evolves, they take these forms. And so you have I minus M inverse A for your relaxation, and then I minus capital pi. This is a projection onto the range of P for coarse grid correction. And so AMG is classically designed for symmetric positive definite matrices. And so when A is SPD, then the A norm, you have an induced A norm, right? And in doing so, if you define R equals P transpose, then you have that your projection is norm 1 in the A norm. And this is great because what happens is that you can't increase your error. So all pi does is it projects everything out that's in the range of P. And as long as that's complementary with relaxation, then you converge well. And at the very worst, coarse grid correction cannot increase your error. In the non-symmetric setting, especially highly non-symmetric, generally you're going to have a non-orthogonal projection. It's very difficult to construct any kind of sparse coarse grid operator and transfer operators where you're orthogonal in any kind of known inner product. And the downside of that is that you can increase your error. And so you might decrease your error in some regimes, but in the bad range of your projection, then you can actually increase your error. And that makes it really hard to get nice convergent methods on some problems because unless your relaxation immediately damps down any error that you increased, you can diverge very quickly. Okay, so notation in algebraic multigrid here, we're using a CF splitting. A lot of this is for simplicity to kind of reduce our freedom. So we take all our degrees of freedom, and this is assuming it's geometric, but the same thing works for a matrix. And we define our fine grid, we split it into F points and C points, and we map the C points down to our coarse grid problem. And so in the algebraic context, we can write our matrices and vectors in a block form. So we have, A takes this 2x2 block structure. P and R, our interpolation restriction, we assume we have an identity over C points and then some other operator over F points. So what this means is that interpolation, we interpolate C points by value from the coarse grid to the fine grid, and restrict C points to C points using the value of the C points plus a linear combination of the surrounding F points. And then script K here, we define as our coarse grid operator. That's R times A times P. And so to motivate kind of non-symmetric AMG and how we pick our restriction operator, let's look at what happens in coarse grid correction to our error. So our error E at any I plus 1, this is the projection times E evaluated I. This is capital pi. And we split our error into error at F points and error at C points. And then we further decompose the F point error into the error that's interpolated, right? Because P, let me go up. P equals WI, so we're going to interpolate from EC up. And so WEC, this is what we capture in our interpolation. And delta EF is everything that we're not capturing. And so we expand this part over here into the part that we're capturing correctly, and then everything else. And then we can combine it into this form. And so in the first part, we have 0 C point error. And then we have however accurately we can interpolate our F point error from our C points, our course grid. Then we have this kind of extra term where it's really our projection pi times this delta other stuff over the F points. And so the idea of the non-symmetric AMG that I'm going to talk about is let's choose R to eliminate this as best we can. So we want to minimize this term because if we do that, then after course grid correction, we have a perfect solution at all your C points. And if you have a perfect solution at C points, then we follow that with some kind of F relaxation to effectively distribute the accuracy from the C points to the F points. And that's how we define the ideal restriction operator. So if we want RA, delta EF and 0 to be 0 for all delta EF, this is uniquely defined up to simple assumptions on invertibility of matrices as this form. So this is what our Z operator should be, minus ACF, AFF inverse. And then again, we have an identity on this part. And so just a side note, remember I commented on non-orthogonal corrections increasing error. If you actually have the ideal transfer operator for restriction, then you can make an L2 orthogonal projection with this very simple interpolation operator right here. In practice, we don't use this because if you're not exact on our ideal, then having nothing on F points can lead to instabilities, but we use very simple interpolation usually. Okay, and then one other perspective to kind of relate it to something people might be familiar with as preconditioning, you can also write AMG, this is a reduction-based AMG algorithm, as a block LDU preconditioner. So remember, 2x2 inverse formulation, if we take our 2x2 matrix and write out its inverse, the whole inverse can be written as this 3-step process, right? And you might notice on the right here, this is ideal restriction. So this is that operator that we're trying to target. And then S here is our Schur complement. And if you work through a bunch of algebraic details, the relaxation and course grid correction combination of AMG, if you use F relaxation, can be written as this form. So our approximate inverse using both steps of AMG looks like a block LDU. And so here's Z, right? That's what we want to approximate ACF, AFF inverse with. Kappa inverse, or script K, this is our course grid operator, so that approximates the Schur complement. And then delta F, this is our F relaxation. And then this W hat is what we call effective interpolation. It combines the effects of F relaxation and your course grid correction interpolation. And if delta F is exact, if you can do a good solve on AFF, then W hat becomes, delta F is AFF inverse, this goes away, and W hat becomes AFF inverse AFC exactly as we have in the exact LDU. And so the big question in all of this is, can we approximate AFF inverse well? And if we can, then we have a good method. If we can't, we're probably hosed. But there's two contexts. One is in the relaxation. So for delta F here, we can use non-sparse approximations. It can be block ILU, it could be inner GM-res, Krylov methods, it could be Gauss-Seidel, something like that, where you can't construct the operator, but you can solve it really accurately. For Z, we have to be sparse, right? Because we're forming our course grid operator K using Z. And so if Z is dense, then we're going to get fill-in and it's not going to work well. And so what we developed is we call approximate ideal restriction. And if you're into the original classical AMG sum-based formulation of transfer operators, for each row of R, each row is going to correspond to a C point in the domain. So that's the C point. We pick strong F points, so all the F points that are strongly connected to the C point, and we solve this basic equation right here. And really what this does on a more intuitive level is it sets RA equal to 0 within a predetermined sparsity pattern. So remember, for our ideal, we want to solve RA times anything right here equals 0. And so what we do is we pick in R a predetermined sparsity pattern, and we say that we're always going to satisfy R equals 0 within that sparsity pattern. And we get fill in elsewhere. You can't solve it exactly, but that's how we define our approximation. And to do that, each row requires solving this small, dense linear system. And so it's relatively cheap and straightforward to form algorithmically. Right, and so the goal, there's two pieces. We use AIR, which is approximate ideal restriction, coarse grid correction, to achieve an accurate solution to C points. And so the idea here is we get a good approximation to R ideal, we get really low error at C points, and then we follow this with F relaxation to distribute this accuracy to the F points in the domain. And we just iterate back and forth. Okay. Reduction-based methods do not always work well. My advisor and some of his students did papers on it many years ago. And if you want to solve diffusion, reduction is hard because AFF for a 2D diffusion equation, AFF inverse is dense and fully coupled, and it's really hard to get a sparse approximation to it. And that's why it had not been used a lot in the literature. Turns out, if you use upwinded discretizations of advection and transport, you can get really good sparse approximations. And so, as an example, let's consider transport on a structured 2D grid. And so think of these as elements, DG elements, and we partition them into C elements and F elements. Then if you think about a standard upwind DG discretization and consider the matrix connectivity of the C element, you only have facet integrals over the upwind faces, right? And so it's only connected to F elements and it's connected to no C elements. And so what this means is that AFF equals ACC equals the identity. So on the very first level of applying a block error, where I mean, we coarsen and form transfer operators by DG element. On the very first level, we exactly get ideal restriction because we can eliminate, because AFF inverse is effectively trivial to form. On the next level, it gets more complicated because you get spread. You get fill in, right? So when we form our coarse grid operator, all of a sudden this C point, which is now our coarse grid, will depend on these three other points as well. And these are all going to be on our coarse grid. But if we have, again, advection, this bottom element, at least for the direction I have advection going right here, shouldn't really affect the solution right here. Because, right, if you follow the characteristic, it's coming off over here. So in the matrix sense, it's connected, but physically it doesn't matter. And that's just intuition. And the inner part of AMG typically finds these connections. And so if we think about it like that, then again, this element on our coarse grid only depends on two other coarse grid elements. And again, we can do a coarsening in a way so that this is a diagonal, AFF is diagonal or almost diagonal. And again, we get a very good approximation to our ideal. And that's how we recurse. And that's why this approximate ideal restriction concept makes sense and works well for upwind discretizations of advection. Okay, and so that's kind of high-level background on AIR. I have plenty of results applying AIR to advection equations, but it's not what I'm talking about today, and you can see them in the papers. So today I'm going to move on to discussing the actual anisotropic diffusion equation. So if we go to DG, now we're a 2x2 DG system, and again, we reorder it. And so this is after discretization, so I've replaced the differential operators with letters indicating the matrices in our weak forms. And so we've reordered, so we have the transport, these scaled GB and GB transpose, those are on the diagonal. And on the off diagonal, we have this mass matrix coupling up here. And down on the bottom left, we have two mass matrices. We have the time-dependent mass matrix and this special boundary condition integral mass matrix. And then we have our isotropic diffusion. And so this boundary condition penalty ends up being order 1. So for the analysis in the next slides, we're just going to denote this as a single M, and it's effectively equivalent in a spectral sense. And so what we do is we apply a block triangle preconditioner to this operator, and we don't even bother with something fancy in the short complement. We just use the diagonal blocks. And so many of you probably know this intuitively anyway, and we wrote a paper on it proving it rigorously. Convergence of fixed point and Krylov is really fully defined by how well you approximate the short complement. And it's not just asymptotic, it's like every iteration you can relate to how well you approximate your short complement. And so here, this is our short complement. We have our gradient, then we have our mass matrix, an isotropic component with the gradient inverse, and then another mass matrix. And so we did a spectral analysis of this, and it's it's interesting when we do this preconditioning because we're working with hyperbolic operators, but after applying the preconditioning, we end up going back to the SPD realm. So if we take our diagonal block, our transport inverse, and apply it to S22, our Schur complement, we get this set of three operators right here. So we have the identity. This is the term corresponding to the anisotropic diffusion. And this is the term corresponding to the anisotropic diffusion. Sorry, the isotropic. This is similar in like a spectral similarity sense to this operator right here. And this is SPD. And in fact, both of these inner terms are also SPD. And so what we're going to do to understand the preconditioner and prove its robustness is to analyze these two terms. So the first term, this is the anisotropic one. This we do really well on. And it's kind of like a loose spectral analysis based on operators and scaling of eigenvalues of operators. But we found in practice it lines up perfectly with what we see. So for a mesh H and constant C1, C2 that are independent of your mesh, the eigenvalues of this operator live in this roughly in this interval. And so H squared corresponds to considering the scaling of the mass matrices and then the advection operators here. And the range goes from H squared to 1 for the eigenvalues of the inverse of the gradients there. And so this is all fine. We have a scaling here. The important thing is we also have a kappa delta in the bottom. So this is the anisotropic component that's going to be really big. And so as long as our delta T is not really small, then this is going to be really small, the eigenvalues of this perturbation here. So the second term in the isotropic one is a little more complicated. And so to kind of motivate it, we take a simple example and explain how this works when you have an isotropic operator preconditioned by the anisotropic. So say we're in 2D and we have a magnetic field B aligned in the x direction. And in that case, this second term right here does directly correspond, but it corresponds with a discrete representation of dxx inverse times your 2D Laplacian, right? And so this is going to be 1 plus dxx inverse dy. And so on a unit domain with zero Dirichlet boundary conditions, you can take the Laplacian eigen decomposition and takes this form. So here UJK are your eigenvectors, and this pi squared, j squared plus k squared are your eigenvalues. And here j and k are the frequency of the sine functions that are defining your eigenvector. And so UJK is 2 sine j pi x and sine k pi y. So again, this is just the frequency of the sine function over your domain. And so this is similar for dxx. And what we do is we kind of by construction, we show how big this eigenvalue can get. And so what we do is if you have the highest frequency in y, so again, this is the orthogonal direction, so not aligned with the magnetic field. So we let k be 1 over h. It's the largest frequency you can represent on your grid. Then we choose the smoothest one in x. So we choose j equals 1, so just a big sine hump in the x direction. Then this is an eigenvector relation of the operator. So remember, this is our preconditioned operator, 1 plus dxx inverse dy. This is our eigenvector where we choose j equal to 1 and k equal to 1 over h. And this is an eigenvector of this operator with eigenvalue 1 plus 1 over h squared. And so this is the really tricky part about anisotropic diffusion. We have these really large eigenvalues that are really smooth in one direction. And they're hard to represent on a coarse grid, but they're also smooth and they're not well attenuated often by relaxation. And so altogether, we can approximate the spectral bound on the second operator as within 0, and then k perp over k delta over h squared. And so this kind of ends up being the problem that as h squared gets bigger and bigger, it damps this k delta more and more. And this h squared comes from the isotropic Laplacian. And so this is the more concerning part. If k delta is not so big, then our method's not going to work so well probably. And this is just combining everything because these are SPD, and this is the identity. We have a bound on the eigenvalues of the whole preconditioned operator. And so again, because it's SPD, we can, in practice, we can actually compute the eigenvalues of the preconditioned Schur complement via Lanczos iteration. And we get really nice agreement with what we derived in theory. And so here's just an example for two different delta T's and then different ratios of anisotropy in 2D and 3D. Then the three columns for each are three mesh resolutions. And so the big thing is what we see that when we go down, so each column here from 10 to the 3, 10 to the 6, 10 to the 9, we do see exactly a reduction in the eigenvalues on the order of this. So the bigger our anisotropy, we linearly scale the eigenvalues of the preconditioned operator, or the perturbation, sorry, because we subtract identity here. So we want these all to be 0. The bigger the anisotropy, the smaller these values get, and it corresponds exactly. And then we have more or less the same thing with delta T. So as we make delta T an order of magnitude bigger, our eigenvalues get an order of magnitude smaller. And so this corresponds exactly with these bounds with these bounds right here, where we have a kappa delta in the denominator and a delta T. And we might be missing a delta T in this equation. I need to check on that. But the point is, for big 10 to the 9 kind of ratios, the eigenvalues away from unity are tiny. So we're really, really, really close to unity of our preconditioned Schur complement. And so to demonstrate it, we choose an analogous problem as for our DG convergence study. And the key here is that we use open field lines. And so when I say open field lines, I mean the field lines do not connect in a circle. And the reason for that is if we have closed field lines and we go back to our directional gradient, the advection operator by itself as a steady operator is not invertible. And that's unfortunate, but it's a problem. And so there's so much kind of conceptual discretization and solver and theory in formulating this. We started with saying, okay, let's try the open field lines and see if we can make it work. And it does. And so this is our first result, and this is what's online in our paper right now. So we use block preconditioned FGM res, outer relative tolerance 10 to the minus 8. We choose an inner tolerance using this kind of interesting relative residual formulation. So it's a minimum of 10 to the minus 3 and 10 to the minus 3 over norm of B. That's bad notation, where B is current right-hand side. B is usually our magnetic field. Think of this as R. This is kind of a nuance that we had to discover. So when you use solvers in libraries, you can often set a relative and an absolute tolerance. Typically, it does not say you want to satisfy both of those. It says you want to satisfy one, and there is some kind of priority. What we really need in this problem is we need to satisfy both. So when you do a block preconditioning and you have inner solves, my experience has always been, about 3 digits. If you bother doing more than that, it's a waste of effort because you're not going to improve the convergence of your outer method. And if you do less, then you might not be solving accurately enough for your outer GM-res precondition to converge. So this is just kind of like a benchmark that I use as an inner tolerance. The problem here is when the lower off-diagonal block with the isotropic diffusion is big, when we get to our second solve of the block preconditioning, the right-hand side provided to it can be really large because it's scaled by this kind of large operator in the off-diagonal, as big as 10 to the 4. And what we found is that if we have a 10 to the 4 right-hand side and you solve to 3 digits, then the residual is not even less than 1 in norm. I mean, it's still order 1 residual, and this causes the outer iteration to fail to converge. And so what we did is we have this modified tolerance to account for the different magnitudes of residual between the first and second linear solve. Okay, and so here's the total inner AMG iterations comparing classical AMG applied to the mixed, so CG2/DG1 discretization, a classical DG2 mixed discretization, second order primal discretization. No, this is mixed, yeah. DG2 without upwinding with classical AMG, and then air applied to our mixed discretization. And so here we show the total AMG iteration count as a function of anisotropy ratio. And what we see lines up pretty much with theory that air does not work very well in our advective formulation when the anisotropy ratio is not very big. So at 10 to the 2, 10 to the 3 is not winning. And you can solve this perfectly well with classical AMG and other discretization techniques. When we get up into this 10 to the 8, 10 to the 9, 10 to the 10 kind of realm, that we expect to see in practice, the improvement of air over the other methods is quite substantial. And so we ran out of time for the finest refinement level on our nodes for both of the AMG, classical AMG problems. And we solved it very nicely with air. And so we have similar plots for wall clock time. So this is wall clock time again for the same classical AMG on the left, 2, and then air on the right. And just for a ratio, we were about 45 times faster in wall clock at this second refinement level than either of these other two approaches to get a solution with good accuracy. And it will probably continue to increase as we continue to refine the mesh, because the scaling of these other methods is much, much worse than the scaling of air. Our scaling is not perfect, but it's not too bad. Okay. So those results are for closed field lines. Difficulties for open field lines. And what we really care about is closed field lines. And there are difficulties with closed field lines. So first off, and most kind of directly relevant, is that the advection operators are not invertible. There's no time derivative on the advection. It's really on the mass matrix and the primal operator. And so we have these steady advection operators. So if those are invertible, then we can't use that same kind of reorder and solve each advection block approach for closed field line problems. And the thing about closed field lines with these extreme levels of anisotropy is, for physical problems, one time step, information traverses a closed field line many, many, many times. And so it's not like you're integrating partially one way around. One time step will do, 100 or 1,000 iterations around your field line, because the ratio, or the heat conduction coefficient along that direction is just so large relative to our time scale. And then the last and most important point is that we will have closed field lines in pretty much all realistic applications, at least in the context of magnetic confinement fusion. So what do we do? So our idea is simple. It's less elegant, and it's harder to prove anything with, but it's that we keep the reordered system, and we just apply air all at once. And so we have this reordered system, and we place the advection blocks on the diagonal. And so at effectively magnetic field line, there's an interface where this becomes a fully coupled and cyclic. So this guy depends on the lower one, and they all cycle around. And without that coupling, then this is not invertible. But it still looks a lot like advection. And if we put it on the diagonal, then AMG and all the parts within AMG and air will act mostly like it's an advection operator. And this is working pretty okay. And I had hoped we'd have more results by now, but this is still ongoing work to try to make the solvers better. So this is what we currently have. And what we compare again is total AMG iterations, the mixed Gunther et al. Discretization with classical AMG versus air applied to our upwinded mixed DG2. And so we compare the AMG iterations and the relative accuracy. And this is on a pretty realistic tokamak test case. So we have 2 toroidal planes. We have physical values for our heat coefficient, our heat conduction values, and 3 refinements of the mesh in the colloidal sense. And so what we have is we see scaling and just far less AMG iterations. So on a very coarse mesh, we have about 3 times less AMG iterations and relatively comparable accuracy. But as we start to refine, by the time we get to a finer mesh with 2 refinement levels, we're between 15 and 20 times less AMG iterations and 6 times more accurate at the same time. And so we're pleased with this. We would like the solver to be better on closed field lines, but as I mentioned a slide ago, when the information is traversing closed field lines many, many times in one time step, the problem is just a lot harder than open field lines. And so if we can get reasonable solver results, at the end of the day, we're pleased with that, because it's a lot better than anything else, as far as we're aware, that's in the literature. And so we're currently exploring better relaxation techniques and other AMG modifications to make this more viable, and also looking at solvers for the mixed continuous case, because with continuous elements, you have less degrees of freedom, so it's cheaper in that regard. And so we'll see how that plays out. Yeah, so to review, diffusion and magnetic confinement fusion is extremely anisotropic, and it follows the direction of your field lines. And at least in many applications, we can't or don't want to have the mesh align with those field lines. And so that makes, if you're perfectly aligned, you can do other tricks to solve it. But if you're not, it becomes really hard. And so we rewrote our diffusion system based on directional gradients, and we applied discretization and solver techniques that are developed for advection and transport within this coupled directional gradient formulation. And in both accuracy and solver wall clock time, we get orders of magnitude reduction over traditional and existing methods. So again, next steps, we want to incorporate this into larger MHD simulations. The first step is just doing nonlinear temperature evolution. So we have a nonlinearity in the diffusion coefficients that depends on temperature. We're still working on better solvers for the closed field lines and also mixed regimes. A lot of what we care about, it stays, it's just going to be 10 to the 9, 10 to the 10. But in theory, you could have problems where that varies dramatically over the course of the domain. And you saw how our existing method was not so good in isotropic regimes. And so we need to think about how to make the solvers effective on mixed isotropic and anisotropic problems. And then last, it's a pretty interesting concept. We've had a lot of fun working on it, and the fact that these discretizations work so nicely in this extremely anisotropic regime and the solvers. And so I'm kind of high level interested if this kind of behavior arises in other applications. Again, my background is math and methods and less applications, but I'm always looking for interesting applications where we can apply new methods to. So if you have any ideas, please feel free to reach out. Yeah, and thank you everybody for coming. These are some of the papers associated with this work. The first two are just old papers from my thesis on air, some block preconditioning theory work, and then the last two are one that's online, a preprint for the DG discretization, and then we're working on our second paper right now. Hopefully have it done in a few weeks. So thank you.
All right. Thank you very much, Ben. Let me give you some virtual applause here. So there was a lot of folks saying in the chat that this is very interesting work. Some of them had to leave, unfortunately. All right, any questions for Ben? Very, very interesting work. Let me maybe start. So these papers, are these on archive? Are these on your website? What's the way to find them?
They're all on archive. And the recent one on the anisotropic diffusion is on archive. It should be on ResearchGate somewhere too. And then we'll submit the second one with the CG elements hopefully in the next month or so. And it'll be on archive too. Yeah.
Okay, so unsurprisingly, maybe how can this work, and how well will it work if you have curved element and high order discretization spaces?
So I think it would work well, and the reason, so there's multiple pieces of that. The purpose of this in the first place was to assume no structure of the magnetic field line with the mesh, and so in that case, going to fully unstructured, going to curvilinear, going to anything like that from the solver perspective doesn't matter. And from the discretization perspective also doesn't really matter. My one concern with going higher order would be negativities. If we get really sharp gradients in the temperature, I don't know if that would be a problem. That's kind of more of a physics question and would depend how low the temperatures really do get in the tokamak. Usually it's high temperature, but if you have a low temperature regime, that could be a problem. But other than that, I think that it would be totally viable. And then from the solver perspective, also, if we use DG, air works great on high order fine elements for transport. It has no problem. It gets more expensive because we do block inverses on the DG elements, but from an iteration perspective, it works great. So
might be really interesting to do some lower refined version of air. But that's a separate topic.
It is. I have tried this, and it's if anybody has ideas, that's a whole separate topic I'm interested in talking about, because I've never, in the hyperbolic case, in advection and hyperbolic, I've never been able to get low order refined to work. I tried a few different contexts. It's actually an interesting question. If it was done, if you did low order refined on the original parabolic problem, and if that would be okay in a way that it's not for straight hyperbolic, because this is not a hyperbolic problem in principle.
Yeah.
So that's an interesting question.
Okay. All right. Other questions for Ben?
And,
a question.
I was gonna say, feel free. Anybody can reach out and email me or Golo if you have questions. We're around.
Chris?
I was just saying, hi Ben, long time no see.
Hey, Chris.
Yeah, thanks for the talk. Really interesting work. And I'm glad to see that you found some success. as you pointed out at one of the beginning slides as to how difficult this problem can be. Yeah, and actually, so that was what my question was about. Is this? Well, first, let me ask just to make sure I understand the last results you showed with the iteration counts. Was that using which problem was that for? When you were showing the error count?
So the plots with the iteration counts were for the problem that we used for the DG test case, which was 3D and periodic in Z, and it had a prescribed initial temperature field that we then used as a steady state, or we formulated the problem in a manufactured way so it should be steady in time, and we use that to and we didn't integrate for a long time, so we're not accumulating time error, and we use relatively small time steps, and then we use that to measure the spatial discretization from the prescribed initial condition that's more or less exact within the fine element space.
Right. Okay, good deal. So then, yeah, my question would be, well, first of all, a compliment and the fact that you got, the code that Milan and I worked on with Elon to even give you an answer at 10 to the 9 anisotropy, because I remember us having a hard time getting the solvers to converge.
It wouldn't. Yeah, I mean, that was in that plot you saw the convergence of both the error and the solver in the 10 to the 9 for the classical AMG and classical discretizations just didn't work. Right.
Yeah. So that was really nice to see that not only that there was convergence, but that there was substantially better. My question, I guess, was: have you tried a test case? So in that one, I was trying to get an understanding of what's difficult there, and certainly there's just the anisotropy. But the initial condition looked relatively smooth. It didn't have any thin filamentary features that you might otherwise see, with a boundary layer being formed in a different magnetic geometry. And I'm wondering if that would almost help you in the sense of when you were talking about that with the last slide with iteration count, get that 1/h². So if you had a boundary layer that you had to resolve, then maybe even at the lower anisotropy ratios, you might start getting a win there just because, the grid would have to refine that boundary layer.
Right, that's an interesting point. So the final test here, which I do not have a picture of, is a pretty realistic tokamak with an X point and everything, and this. Right. This would have that. And that's also why the accuracy is a little more erratic in the sense that, we go down by a factor of 5 and then we go down by a half, even though we should be getting something like third order convergence here. I don't know why that is. It's hard to say. There's a lot of stuff going on in that problem. So we've done a little bit of that, and that's pretty high on the priority for after we finish this paper on the CG discretization is hopefully moving to FEM. And I'm trying to get a better version of AIR in a parallel AMG library connected through FEM. And we're thinking we're going to try to do a benchmarks kind of paper where we look at discretization and solver and really understand what can be done on more realistic physics. And yeah, so hopefully next year.
Yeah, good deal. Looking forward to those results. Thanks.
Yeah, me too. Thanks, Chris. Any other questions for Ben? All right. Well, we'll post the slides. We'll post the recording. I know some folks had to leave early, so I'm sure they'll watch it later. And Ben will reach out if we have questions. I definitely will look at your papers and think about this in more detail. Maybe there are some connections where we can collaborate.
Yeah, that'd be super cool.
All right.
Great.
Thank you.
Thanks, Daniel. Thank you, everybody.
Thank you, everyone, for coming. We'll meet again in about a month.